Okay, so in the last lecture, remember we spent the majority of time discussing how to solve the boundary value problem for Laplace's equation on rectangles in the plane using all the theory we have for Fourier series. And then in the second part of, or in the final minutes of the lecture, we introduced the next problem we're going to consider, which is solving the boundary value problem for the Laplacian in a disk in the plane. Right, so our domain for the first part of the lecture will be a disk, which I'll call d sub a. And so this is the disk of radius a centered at the origin. Right, and so in polar coordinates, you can describe this disk as just the set of points, say r theta with radius between 0 and bigger than or equal to 0 and strictly less than a. And the angle theta is going to be between 0 and 2 pi, right? You can also use standard Cartesian coordinates to describe this disk. So this will be the set of points x, y with x squared plus y squared strictly less than a squared, right? And so what we're interested in understanding is how to solve the Dirichlet boundary value problem for Laplace's equation in this domain. So more specifically, we want to find a function u such that the Laplacian of u is equal to 0 inside the domain, and also that on the boundary u is equal to some specified function h, right? And so of course, in polar coordinates, the boundary has an easy description. It's just where the points where the radius is equal to a, right? So this is just describing the circle of radius a centered at the origin, which is the boundary of this disk. In standard coordinates, you can also describe the boundary as the set of points x squared plus y squared equals a squared, right? And so we saw that the main idea here is to observe that, well, your domain here is rotationally symmetric, and we have all these nice rotational invariance properties for the Laplacian, and we also have a good way to describe the Laplacian in polar coordinates. And moreover, the formula for the Laplacian in polar coordinates does not mix any of the derivatives in terms of like derivative with respect to r and derivative with respect to theta. And so since that's the case, this indicates that we should be able to get somewhere by using separation of variables with respect to r and theta, right? And so we discussed this a little bit at the end of the last lecture. And so this is what we're going to do now. One thing to point out is, well, let's say we know that, let's just review what we need for the boundary condition, right? So we want u equal to this function h on the boundary, right? Well, on the boundary, if we use polar coordinates, on the boundary, we have u is a function, well, excuse me. If we use polar coordinates, u of r theta is given by, well, the boundary is where we set r equal to a, right? So a is some fixed number. For example, you can view a as equal to 1 if you want to, or a is 2. Right, but the boundary is exactly where the radius has been fixed to whatever this number is. And so the only variable is theta, right? Right, on the boundary. Right, and so in particular, we can parameterize the boundary in this way by using the angle theta and view functions on the boundary as functions of theta. Right, so we can view the function that was given to us, h, as just a function of theta. Right. Right. Well, the issue with this is that, well, let's say I start when theta is equal to 0 over here, as we saw last time. Well, as I let theta increase between 0 and 2 pi, you're gonna move around the circle as theta varies. But as soon as theta hits 2 pi, I'm gonna come back to where I started, right? And similarly, let's say I start at this point over here and I increase theta along the circle. Well, if I keep increasing theta, eventually I'm gonna come back to the same point, right? And so in order for this to be well-defined, we want to require that the function h is periodic. Otherwise, you're gonna run into some issues with this related to this observation, right? So we need to require, for example, h of 0 to be equal to h of 2 pi. And more generally, if we look at some point theta, right, let's say this is this is, say, some particular point theta. Well, over here, this is theta plus pi, right? But then if we do theta plus 2 pi, right, we get back to the same point, right? And so in order for this function h to be well defined, we need h of theta to be equal to h of theta plus 2 pi, right? So and more generally, we need h of theta equals h of theta plus 2 pi for any theta, right? So h needs to be 2 pi periodic as a function of theta, right? And so let's add this condition here. So h is equal to h of theta, which is 2 pi periodic. Otherwise, the boundary condition is not kind of well defined, and it's not clear how to proceed because the function h isn't really doesn't make sense as a function anymore. Okay, and so now let's, with that kind of technical extra condition we need for the boundary function, let's proceed and actually start solving the problem. And again, we're going to work in polar coordinates, right? And so let's begin. So let's guess, well, let's proceed with separation of variables. Again, and now we're using the variables r comma theta instead of x comma y, right? So we're using polar coordinates. And so we're going to guess that my function u as a function of r and theta is equal to some function f of r times some function g of theta, right? Well, we have 0 is equal to the Laplacian of u. Well, remember the Laplacian in polar coordinates takes the following form. I have second derivative with respect to r plus 1 over r times second derivative with, or first derivative with respect to r. And then finally, plus 1 over r squared times second derivative with respect to theta, right? So if I guess that my function u has this form, I can write the Laplace's equation in this manner. And so if I now apply these differential operators to the product of f of r and g of theta, I end up with 0 is equal to, well, this is why separation of variables is useful in this case, because notice that each of these acts on only one variable, right? If we had some differential operator here that involved derivative of r and derivative of theta simultaneously, then maybe this technique wouldn't be as useful. But here this will actually allow us to separate the different variables, right? And so the first operator gives us f prime prime of r and leaves g unchanged. The second operator here will give us 1 over r times f prime of r, and again, leave g unchanged. And then the final operator here will give us 1 over r squared. It'll leave f unchanged, and then I'll get g prime prime of theta, right? And so if u has this special form, then the Laplace's equation in polar coordinates reduces to this equation. And now we're going to convert this to two ordinary differential equations in r and theta separately, as we've done several times by now. Right, and so what we want to do now is let's rearrange this equation. So we have to do a bit of algebra. One thing I'm going to do is, well, we don't like dividing by powers of r, so let's just multiply through by r squared, right? So if I multiply by r squared, we end up with 0 is equal to r squared f prime prime of r g of theta plus r f prime of r g of theta plus f of r g prime prime of theta. And so now let's move the first two terms over. So we end up with minus r squared f prime prime of r plus f prime of r times r. And I'm going to factor out the g of theta, right? So this is from the first two terms. I'm going to move them over to the other side, right? Notice that both of these have g theta here, so I can factor this out. And this is all equal to what's left over. I get f of r times g prime prime of theta, right? So we're trying to get all the terms that depend on r on one side and all the terms that depend on theta on the other side. Well, now it's clear how to do this. So finally, we end up with, right, let's divide by f of r and g of theta. right? So we end up with negative r squared f prime prime of r plus r f prime of r divided by f of r is equal to g prime prime of theta over g of theta. And since r and theta are separate variables, of course, this has to be equal to some constant, let's say minus lambda, where this is constant. Right. The reason I'm putting I mean, this is kind of an arbitrary choice. The reason I'm putting a minus sign here is just because we have a minus sign here. But right, so it's just equal to some constant. Right. Using again the same argument we've seen many times by now, since I have a function of r equal to a function of theta, and these are separate variables, the only way this can happen is if they're both constants and independent of either variables, right? And they have to be equal to the same constant. Right? Okay, well, this leads to the following two ordinary differential equations. Right, so we have the first ordinary differential equation, which is in terms of theta. Well, we have g prime prime of theta is equal to negative lambda times g of theta. So g prime prime plus lambda g of theta is equal to 0. And then the second ordinary differential equation, which is a little bit more complicated, will come from the r terms. So we end up with, if you do the algebra, the minus signs will cancel. So I have r squared f prime prime of r plus r times f prime of r is equal to lambda times f of r. And so let me bring that term over. So I get minus lambda f of r is equal to 0. Right. So these are the two ordinary differential equations that we need to solve. Again, this is why separation of variables is so powerful, because we've taken a partial differential equation in some domain in the plane, and we've reduced it to two separate ordinary differential equations, which are easier to solve than partial differential equations. Right, so at least the first equation here looks very familiar, hopefully, because we've dealt with this equation many times in all of these separation of variables arguments. So for one, well, let's just use the standard solution and that we've had so far and hope that this works. So I can solve with g of theta is equal to a times sine of something plus b times cosine of something, right? So this is the structure of the general solution. And let's suppose, using our intuition from all the other separation of variables problems we've looked at, let's suppose that lambda is equal to n squared, where n is an integer, say bigger than 0. Right, so then the solution would be given by sine of, or bigger than or equal to 0, say. Solution would be given by sine of n theta, a times sine of n theta plus b times cosine of n theta. Right? Right, and so now let's move on to the second equation. Right, so for the second equation, well, this is a little bit harder to approach using just, I mean, you're not gonna be able to solve it using some combination of sines and cosines, so we need another method to solve this. Well, one way to solve this particular type of ordinary differential equation, if you think back to earlier classes, is, well, let's try to guess that the solution is given by maybe some power of r, right? So let's guess that f of r is maybe some number c times r to the alpha, where alpha is some number, right? Well, let's plug this into the equation and see if we can determine what alpha has to be, right? So if we plug this in, well, let's first suppose that, right, so actually let's just plug this in first, and then I'll add some conditions, right? So if I plug this in, we'll notice that I get, well, f prime prime of r has to equal c times alpha times alpha minus 1, r to the alpha minus 2. F prime of r has to equal c times alpha times r to the alpha minus 1, right? And so if I plug these into our equation, we end up with r squared times c alpha minus 1 r to the alpha minus 2 plus r times c alpha r to the alpha minus 1, and then minus lambda f of r. Right, is all equal to 0. Sorry, f of r is just c times r to the alpha. Well, now if I simplify this a little bit, notice that I have r squared here and r to the alpha minus 2 here, so I'm just going to get r to the alpha, and similarly here. So this implies now that I have c times alpha minus 1 r to the alpha plus c alpha r to the alpha minus lambda c r to the alpha is equal to 0. Right? And so now let me divide by c times, right? So each of these things I can divide by, right? Let me eliminate common terms. And so I end up with now, well, we want to figure out what alpha has to be, right? And well, I get the following equation: alpha times alpha minus 1 plus alpha minus lambda is equal to 0. And therefore, alpha times alpha minus 1 plus alpha has to equal lambda, right? Well, we're assuming that lambda is a particular integer squared, right, where n is some integer, right? And so, well, now we're almost done. Well, let's first consider the case where, well, actually, I can simplify this a little bit further. So this here is alpha squared minus alpha plus alpha, and so we end up with finally alpha squared has to equal lambda, which is n squared, right? And so this tells me that alpha should equal plus or minus n, right? Right, and so, well, this gives us, well, let's say n is equal to 0. Well, this tells us that if alpha is equal to plus or minus n, then alpha is just equal to 0. And so our choice would be just some constant c. If n is bigger than 0, we end up with f of r is given by some number c times r to the n, or some number c times r to the n minus r to the minus n. But remember, the equation is linear, right? So if I have two different types of solutions that work, I should add them together to get a more general solution, right? And so we can solve this by taking some combination, say c1 times r to the n plus c2 times r to the minus n, right? And so it turns out that actually when n is equal to 0, this is not the most general solution to the ordinary differential equation. It turns out that you can add a logarithmic term, right? So you can actually add some number d times log r and still solve. You can just see this actually directly by going back to this equation and trying to solve it when using a separate method when lambda is equal to 0, right? You can just look at this ordinary differential equation and you can show that log r is also a solution when lambda is equal to 0. Constants are also solutions as well, which is what we got in the previous argument. However, notice that, well, log r, right? So let me actually add this on, right? So the more general solution is plus some number d times log r more generally. So why didn't I do this initially? Like, why haven't I spent more time precisely deriving this log r term? Well, we'll notice that r is allowed to be equal to 0 in our domain, dA, right? Because the disk is centered at the origin, right? Right, so say this is our disk. right? So this is the origin is the center of our disk. But when r is equal to 0, log r, it blows up, right? So log r is singular at r equals 0. Well, likewise, if we look at the solutions here when n is bigger than 0, there's also a similar issue, right? So is r to the minus n is singular at r equals 0 when n is bigger than or equal to 1, right? Which is a wide range, which is admissible in what we're considering. And so in order for our solution to not blow up or be infinite at the origin, we need to eliminate these terms, right? So we need to cross out this term and cross out this term, right? So we want to eliminate. So u of 0 theta is not infinite, right? So the point here, just to recap what was just going on, is, well, it's true that this combination of functions is the most general solution to the ordinary differential equation for f that we have up here, right? For this ordinary differential equation. The only issue is that if we try to build our solution u using this as our function f, then the solution could be infinite at the origin, right? And so we don't want our solution to be infinite at the origin because we want it to be defined everywhere inside the domain. And so we have to take C2 equals 0, right? So we're going to take C2 equals 0 to eliminate that part, right? And similarly, we want to get rid of this log term because otherwise the solution could be infinite at the origin. And so this gives then finally well, as a candidate for u, we have, well, f was c times r to the n, right? This is f of r. And g was a times sine of n theta plus b times cosine of n theta, g of theta, where n is just any integer bigger than or equal to 0. Right. And so, of course, we all know what to do now. So we found a particular solution, ignoring the boundary conditions, right? But we found a particular harmonic function in the domain for each integer n, right? And so to get a more general formula, we want to sum overall n bigger than or equal to 0, right? So this leads to the more general solution formula, u of r theta given by now sum from n equals 0 to infinity, c times r to the n times a sine theta, plus b cosine of n theta, where a and b can depend on n, right? And so what I can do is, well, since an or bn are certain constants which may depend on n, and then I have another constant here, say cn, let me just absorb this constant here, multiply through. And so I can rewrite this now as just, right, I'm just redefining the constants. I can write this as r to the n times an sine of n theta plus bn cosine of n theta, right? And so this is our solution formula now in polar coordinates for, right, so this is harmonic in the domain dA, right? And so as you can see, the theory of Fourier series is going to be very relevant here because we've written down a particular Fourier series, right? With this modified extra term here, r, right? So if we fix r, this is a Fourier series in theta, right, for each fixed r. Okay, up until this point, we haven't used the boundary condition, right? So let's use the Dirichlet boundary condition. Right, because we don't just want a harmonic function, we want a harmonic function that's equal to h, the given function h, when r is equal to a, right? We want u of a theta is equal to h of theta, right? well, let me just plug this in into the above formula, which we just derived. So we need h of theta should be equal to u of a theta, right? So this is equal to now the sum from n equals 0 to infinity of a to the n an sine of n theta plus a to the n times bn cosine of n theta. Right. Well, if we look at the first term here, then this is the sine Fourier coefficient of h as a function of theta, right? On the other hand, a to the n times bn has to be the cosine Fourier coefficient of h of theta. Again, we're viewing this as a function of theta now, where theta is the angle in polar coordinates. And so the Fourier series is defined with respect to theta, right? But we know how to calculate these coefficients in terms of h, right? And so in particular, we're on the domain theta is between 0 and 2 pi, right? And so let's just use our formulas. So therefore, we need a to the n times capital A of n is equal to 1 over pi times 0 to 2 pi, h of theta times sine of n theta, d theta. And likewise, a to the n times b sub n is 1 over pi times integral from 0 to 2 pi, h of theta times cosine of n theta, d theta. Right, these are just the full Fourier coefficients on this particular interval. Well, now I can, in order to find an and bn, I can just divide by small a to the n, right? So capital A to the n, the sine coefficient is given by 1 over a to the n times pi, and then times this integral. And then bn is given by 1 over a to the n times pi times this integral. Right? And so these are how we find our coefficients in the above formula. Right? And so now the solution formula is, well, our function u is given by this infinite series with an and bn respectively equal to these integrals, right? So these are like Fourier coefficients, but divided by the radius of the domain to the n, right? Okay, and so if you watched the last lecture, I promised that for the Dirichlet boundary problem on a disk, we're going to have a simpler formula than what we had for the rectangle case. But this looks kind of almost as complicated as what we had in the last case, right? Because we have this infinite series here, and these coefficients are these kind of Fourier coefficients could be in principle hard to calculate in terms of h, depending on what h is. So this doesn't seem like a very simple formula. Well, it turns out that, and this is kind of surprising, it turns out that this formula can be dramatically simplified. And so this is going to lead us to a much more tractable solution formula. And so our next goal is now simplifying the formula that we just derived. Yeah. Okay, and so let's begin with this. So what we want to do is now plug in the formulas we have for an and bn, right? And so if I plug these formulas in, we end up with, well, u of our theta is equal to, let's say we have 1/2 a sub 0, and then plus the terms when n is bigger than or equal to 0. So sum from n equals 1 to infinity. Well, we have r to the n, which was already there. And we'll notice that in each of these coefficients, we're dividing by a to the n times pi, right? So let me just factor out the 1 over pi. And then I have r to the n over a to the n, right? And then I'm left with, well, in the first term, I have integral right? So in order to not confuse us with, right, so we're gonna have to insert these integrals for an and bn, right? But we already have a theta floating around in the formula. And so in order to avoid confusion, let me change the variable of the dummy variable of integration here. Let's say the dummy variable is, we use phi instead, right? So let's say this is sine of n phi. Right? This doesn't mean we're using spherical coordinates, right? This just means I'm changing the dummy variable, right? That's all this is. Right? Just to it, you'll see why in a second, right? And so now I want to plug these formulas in now for an and bn respectively. So if I replace an, I end up with, oh, sorry, this should be b sub 0. Right. So if I replace an, I end up with integral from 0 to 2 pi. I have h of phi sine of n phi times sine of n theta d phi, right? And then the second term now is the integral from 0 to 2 pi of h of phi times cosine of n phi times cosine of n theta, right? Integrating with respect to phi, right? And so now let me combine everything here. So we end up with u of r theta is equal to 1/2 b naught plus 1 over pi times the sum from n equals 1 to infinity. Let's combine these two integrals. We get r to the n over a to the n, integral 0 to 2 pi, h of phi times cosine of n phi, cosine of n theta, plus sine of n phi, sine of n theta, d phi, right? And so what I'm going to do now is I want to bring in this constant term here into this domain. So I can do this in the following way. Well, remember that 1/2 times b0 is given by 1 over 2 pi times integral of just h of phi d phi, right, on this domain from 0 to 2 pi, right, using our formula for the cosine Fourier coefficient. And so I can actually rewrite this in this manner and then absorb it in here. And so what I'm going to do is, well, since we want to divide by 2 pi for the sake of normalization, because I have a 2 pi here, I'm going to divide by 2 here and multiply everything by 2 here, right? And so then I can actually now combine these formulas. And so we end up with finally u of r theta I can write as 1 over 2 pi times the sum from n equals 1 to infinity of integral from 0 to 2 pi. And then I have r to the n over a to the n times h of phi, and then times these terms, right? Cosine of n phi, cosine of n theta, plus sine of n phi, sine of n theta, all multiplied by 2. Right? Right, all multiplied by 2 plus, and then plus the remaining term 1 over 2 pi integral from 0 to 2 pi h of phi d phi. Right, and so now what I'm going to do is I'm going to switch the order of the sum and integral, which we're just going to assume that we're allowed to do. There's some technical conditions on h which are required in order to do this. Let's just assume that we can switch the order of the sum and integral. And so what we're going to be able to do then is, well, once I switch this order, I have an integral from 0 to 2 pi of something over here, plus another integral over here. And so I'm going to combine everything into one integral, right? In order to make this a little bit easier, what we want to do is, well, notice that I can simplify this a little bit, right? So this is equal to cosine of n theta minus phi using the double angle formula, or the sum of angles identity for trig functions. Right, and so I can finally write u of r theta as, well, it's 1 over 2 pi times, or let me switch the order of the integral and sum, excuse me. So it's the integral from 0 to 2 pi, 1 over 2 pi. And then I have 2 times, or sorry, I have the sum from n equals 1 to infinity of 2 times r to the n over a to the n h of phi cosine of n times theta minus phi. Right, so this is my infinite sum, and then I have plus h of phi d phi. And well, just simplifying this a little bit further, this tells me that u of r theta is 1 over 2 pi integral from 0 to 2 pi. And then I finally have h of phi. Right, notice I have an h of phi term in both of these, so I can factor it out. And then I end up with 1 plus 2 times the sum from n equals 1 to infinity of r to the n over a to the n cosine of n theta minus phi d phi. Right. So up until this point, I've done a bunch of algebraic manipulations and used a certain trig identity to rewrite the infinite series formula we had. It still doesn't look much simpler than what we started with, right? So this doesn't appear to be that we've really done anything other than just combine the cosine and sine terms using this trig identity. Well, the surprising thing is that we can actually sum this infinite series and write down an explicit value of what this is equal to, right? And so this is what we'll do. Right, so we can calculate the sum. Right, and so, well, the best way to do this is to use complex exponentials, right? So let's use complex exponentials. In order to calculate. In particular, we're going to use the identity, well, you have cosine of n times theta minus phi. This is equal to using our identity that allows us to write cosine as some combination of complex exponentials. This is equal to e to the I n theta minus phi plus e to the minus I n theta minus phi divided by 2, right? But I can rewrite this now as e to the I n theta, e to the minus I n phi plus e to the minus I n theta, e to the I n phi over 2, right? And so I'm going to plug these in here, right? Plug this in here, right? Right, so the term in brackets, let me use blue brackets just to indicate, right, what we're focusing on, right? We're focusing on this term, right? So this term is equal to, well, I have 1 plus, well, notice that I'm dividing by 2 here and I have a 2 here, so those are going to cancel out. So I end up with 1 plus the sum from n equals 1 to infinity. Well, let's consider each of these terms separately corresponding to this exponential and this exponential. So I'm going to get 2 infinite sums. The first sum is the sum from n equals 1 to infinity of r over a to the n times e to the I n theta, e to the, e to the I n theta minus phi And then the second term is the sum from n equals 1 to infinity of r over a to the n times e to the minus in times theta minus phi. Right. But what I'm going to do is write this as a geometric sum, right? So we're going to see very soon that this is a geometric series, and well, we have a solution formula for geometric series, so I can plug that in and actually evaluate both of these things, right? So this is equal to 1 plus the sum from n equals 1 to infinity. I can write each of these terms as r over a times e to the I theta minus phi, all raised to the power n, right? And similarly, my second sum is the sum from n equals 1 to infinity of r over a times e to the minus I theta minus phi to the n. Right. And so, well, now, right. So now, as I just said, we're left with two geometric series, right? So let's review for a second how you would calculate one of these things. Well, let's recall if, let's say I have some number x, which is an absolute value less than 1, we have 1 plus x squared plus et cetera, which is the sum from n equals 0 to infinity of x to the n. Well, this is just given by 1 over 1 minus x, right? This is how you sum a geometric series as long as absolute value of x is smaller than 1. Well, we're going to apply this with x is equal to r over a times e to the I theta minus phi, and also x equals r over a times e to the minus I theta minus phi. Right? Because, I mean, this is exactly what we have, right? So this is like our x, right? And we're looking at the sum of x to the n as n goes from 1 to infinity, right? The only thing to be careful of is that we're starting here at n equals 1, right? Rather than n equals 0. Right, so in particular, this says then, if we want to start with n equals 1, this says that x plus x squared plus et cetera, which is the sum from n equals 1 to infinity of x to the n, this is equal to 1 over 1 minus x minus 1. And you can see that this simplifies to x over 1 minus x. Right? And so this is the formula we're going to use. Well, in order for this to be valid, we need to check that the absolute value of the term where the sum end is less than 1, right? Well, that's easy to check here. So notice that if I look at absolute value of r over a e to the I theta minus phi, this is just equal to absolute value of r over a, since the complex absolute value of an exponential is just 1. But this is less than 1 because r is less than a inside the domain. Right? And so this is actually not true on the boundary. On the boundary, r is equal to a, and so it could be the case that this is equal to 1 on the boundary, in which case, or sorry, this is equal to 1 in absolute value on the boundary, in which case this may not converge, right? So the formula we're going to write down is only valid in the interior of the domain, but this is okay because we're just trying to find a harmonic function inside the domain, and then we can think about the boundary condition in like a suitable limiting sense, right? And so similarly, this term here in absolute value is less than 1 as well. So this infinite series will converge for the same way reasons. Right, and so now what we'll do is just plug in these formulas, right? And we'll be able to evaluate both infinite sums. Right, so we end up with u of r theta. It's given by 1 plus, well, I have, in the first term, I have r over a e to the I theta minus phi divided by 1 minus r over a e to the I theta minus phi. Right, so this is the first formula here applied with x equals r over a times e to the I theta minus phi. And then the second sum, I get an analogous term. So I have r over a now with the negative power, e to the minus I theta minus phi, over 1 minus r over a e to the I theta minus phi. Right, and so in order, now what we want to do is just combine these to try to simplify the formula a little bit more. Sorry, this is not u. This is the bracket term, right? Right. So if we go back to our formula for u, what we've just calculated is this stuff here, right? And so what I want to do now is simplify it a little bit further, and then we'll have an integral formula for u, which will be a lot easier to work with than the infinite series formula. Right, so let's now do the algebra and try to combine these terms. In order to simplify the calculations, let's say I'm going to let a be theta minus phi, right? And so we want to calculate or simplify 1 plus r over a times e to the I a over 1 minus r over a e to the I a. Let me use b so that I'm not constantly confusing with two different a's. Right? So b will be theta minus phi, right? And so I want to calculate the sum of all these terms, right? And so in the second term, I have e to the minus ib over 1 minus r over a e to the minus ib. Okay, and so right, so now I have to, again, this is going to be some maybe obnoxiously complicated algebra, but now at this point, it's really just combining complex fractions. And so there are a few algebraic tricks which will make this a little bit easier. We'll see. Well, let me replace one, right? I need to combine like denominators, right? So I'm going to end up with some fraction divided by, with numerator divided by this quantity times this quantity. So let me write one as 1 minus r over a e to the ib times 1 minus r over a e to the minus ib divided by itself. And then similarly, let me do the same thing for these fractions. So I have 1 minus r over a e to the ib, 1 minus r over a e to the minus ib times r over a e to the ib times 1 minus r over a e to the minus ib, right? So that's the second term, right? So this is first term, second term, and then the third term. Let me do this below here. Right, so plus now we have in the denominator we have the same thing. Right, and then in the numerator we'll have now r over a e to the minus ib times 1 minus r over a e to the ib. Right, and so this is term 3. Right. Okay, but these simplify a little bit, right? So in let's look at the second term, for example. Well, if I multiply through r over a e to the ib times these terms, I end up with, well, this should be equal to just r over a e to the ib. Well, notice that e to the ib times e to the minus ib is just 1. And so I just end up with minus r squared over a squared, right? Similarly, the numerator in the third term is given by r over a times e to the minus ib and then minus r squared over a squared, right? And so now if I combine all these terms here, I end up with finally, well, in the denominator, I have 1 minus r over a e to the ib, 1 minus r over a e to the minus ib. And then in the numerator, I have the first term, which I'm just leaving alone. And then I have plus r over a e to the ib plus r over a e to the minus ib, and then minus r squared over a squared. Okay. Now let me clear up some of this. I don't want any fractions in the numerator, so let me multiply through by a squared. And so this is equal to, well, let's first see what's in the, let's multiply out the, before we do any of that, let's just multiply out all of these terms in the numerator and denominator that we haven't calculated yet. So in the numerator, we end up with, well, let's multiply this out. We get 1 minus r over a e to the minus ib minus r over a e to the ib, right? And then finally, we have plus r squared over a squared, right? And then, well, a lot of that's going to cancel out with what we have already, right? I have r over a e to the ib plus r over a e to the minus ib minus r squared over a squared. Right, sorry, there should have been a second r squared over a squared. Right? This is why I just paused for a second. Right, because we had two of these here, and when I copied it over, I only had one. Right, so we have minus r squared over a squared again. Well, a lot of those cancel out, right? So I have minus r over a e to the minus ib, and then I have positive r over a times e to the minus ib. And similarly, I have negative r over a times e to the ib, and then positive r over a times e to the ib. And then finally, well, I have positive r squared over a squared, and then minus 2 r squared over a squared. So two of those will cancel. And so I just end up with 1 minus r squared over a squared, right? So right. So I realize a lot of this algebra may be a little bit tedious, in particular dealing with all of these terms here. But at the end of the day, it ends up being kind of surprisingly simple, right? And so now let's see what happens in the denominator. Well, in the denominator, I end up with, well, I have 1, and then I have minus r over a e to the minus ib minus r over a e to the ib, and then plus r squared over a squared times, well, e to the ib times e to the minus ib will just give me 1, right? And so this is what I'm left with. And so finally, I end up with 1 minus r squared over a squared divided by 1 plus r squared over a squared minus r over a times e to the minus ib plus e to the ib. Right. And so now let me multiply through by a squared just to clear up some of these fractions. So this ends up being a squared minus r squared over a squared plus r squared minus ar times the terms in parentheses. Well, notice that the terms in parentheses are equal to just 2 times cosine of b, right, by our cosine and complex exponential identity. So this ends up, excuse me. So this ends up simplifying to 2 times cosine b, right? Right. And so finally, well, remember that b is equal to theta minus phi. So at the end of the day, we end up with, well, this term in brackets from earlier is equal to a squared minus r squared divided by a squared plus r squared minus 2ar cosine theta minus phi. Right. Okay, so that was kind of a very tedious calculation, but it's interesting in the sense that we had this kind of infinite series here. Previously, we weren't able to go very far with our infinite series solutions, but now we have what's called more of a closed form solution, right? And so I'm going to be able to plug in what we just calculated for this term here. And so if we take the term that we just calculated and plug it in, what do we end up with? Right, so plugging in into our formula for u, we end up with u of r theta is equal to, well, the term a squared minus r squared doesn't depend on theta, so I can factor, or phi, sorry, so I can factor this out of the integral. So I get a squared minus r squared over 2 pi, and then we had an integral from 0 to 2 pi. We had our boundary function h, and then we had this fraction, which is the remaining piece, 1 over a squared plus r squared minus 2ar cosine theta minus phi. And we're integrating with respect to phi, right? And so this is at the end of all of this work, this is our solution formula, right? So this solves the Dirichlet boundary value problem in the disk, where h is the boundary function, right? And dA is a disk of radius a centered at the origin, right? And so the good news here is that we don't have to worry about calculating Fourier coefficients, right? So a lot of what we did really was some analysis of the Fourier coefficients. And it turns out that in this very special case, we can sum the Fourier series and end up with this particular solution formula, right? And so if you're solving the Laplace equation inside a disk, you don't have to use Fourier series anymore because you just have to calculate this integral, assuming you know the boundary function h, right? So you're given this particular boundary data, you just calculate this integral as a function of theta and r, and then you have your solution formula, right? Okay, so I think that's a good place to stop for today. What we're going to do in the next lecture, at least in the first part, is examine some consequences of this formula. So by the way, this is typically called the Poisson formula. Right. And so in the next lecture, we're going to analyze this formula further and look at some consequences. In particular, we're going to study what happens if we go back to Cartesian coordinates, right, in terms of x and y. Right, so here we're using polar coordinates. What does this formula look like in terms of x and y coordinates, et cetera? So we'll address these questions in the next lecture. Right. All right, so if you actually did watch that whole very long calculation, thank you for paying attention. I realize that some of these calculations are very long and tedious, but they're kind of important to see at least once to understand where these formulas come from. I mean, you don't want to be in a position where you're just memorizing formulas without understanding like where they come from, because I mean, sure, that can get you to a certain point, but if you ever need to do anything that requires some original thought or innovation related to an engineering problem or a numerical problem related that involves partial differential equations, in order to do something new, you have to understand how the old things work. It's not enough to just know what the formulas are, right? If you want to do something new, right? So it helps to learn where these come from. Okay, so that's it for today.